Hello, Professor. My name is Youngjin Kim, a second semester student in the Integrated Master PhD student. So today, in this video, I'm gonna talk about the project I selected. The project is titled Pure Water, and it predicts drinkable water using machine learning. First, project introduction. The goal is to develop a machine learning model to determine drinkable water based on various water quality indicators. There are three main motivations behind this project. First, public health improvement. Access to clean drinking water is a fundamental right for all and a critical aspect of public health. However, many regions still struggle to access safe drinking water. Second, environmental protection. Water pollution is closely linked to environmental degradation, and contaminated water can cause severe harm to both humans and nature ecosystems. Finally, sustainability. The cause of pollution and water quality vary across regions, necessitating tailored management strategies that are adapted to the specific water characteristics of each area. Next, here is the dataset description. Dataset details are as follows. First, the trained dataset consists of 1,605 A samples and is used to train the machine learning model. And it allows to run the relationship between various water quality indicators and potabilities. Next, validation dataset consists of 201 samples. It used to evaluate the model's performance during training, helping to adjust hyperparameters and prevent overfitting. Finally, the test dataset consists of 202 samples. It used to access to the model's final performance, evaluating how well the model protects the potability of water in practice. Okay, now here is how I improved this method. First, change the model. I changed from the XGBoost model to the right GBM model, which should provide better performance, and explore a wider range of hyperparameter section. Currently, the range of hyperparameters such as running rate and maximum depth is rather narrow. If we fine-tune the running rate or adjust the depth, we can make the model more expressive. Next, select the attributes based on attribute importance. Not all attributes contribute to the model performance, so removing low importance attributes or reducing highly correlated attributes can improve generalization performance. And handling data imbalance. If there is an imbalance between classes, certain classes may perform poorly. In this case, adjust the scale post weight parameters to imbalance the imbalance. Last, increase cross-validation fold. He performed cross-validation with CV equals 3, but I set this value to 5. So, here is experiment section. In this section, I'm gonna describe the previous model and my improved method in comparison to each other. As I mentioned before, I changed the model and change the hyperparameters such as learning rate, max depth, gamma, and added the scale pulse weight parameter to optimize the model performance. In this following result section, I evaluated the performance on the validation dataset and the test dataset. Compared to the previous model, my methodology improved performance on both the validation and test datasets. Here are the calculated results for the confusion matrix. From this, we can see that my improved method performs slightly worse for the labeled 0 than the previous model, but it performs much better for label 1, which I believe is the reason for the overall improvement. The classification reports for each of the following classes also support the results of the previous calculations. Although the results for label 1 on precision are slightly lower, my method is still outperforming the previous model on the other recourse and F1 score metrics. Finally, here are the ROC accuracy score results, which show improved performance over the previous ROC accuracy score. This shows that my method has improved in several areas over the previous model, which confirms the success of the project. So, this is end the presentation. Thank you for your attention.